Welcome back. So last time we introduced the idea of a function. We did so by first talking about a relation, what it meant for a relation, and what it did. A relation, again, is just a mapping or matching or correspondence, where it's taking stuff from one set A and matching it up with stuff in a set B. And those things actually could be the same things as they are in this example, or they could be different things. We reviewed the idea of domain and range as well. And then we looked at the fact that there are situations where we need things to be a little more restrictive than what a normal relation does. Normal relation allows your input value to have as many outputs as it wants. But in a place like a supermarket, we would not want that to happen. We would not want to have that relationship. So we define a new object which has this idea of being well defined. Just like our arithmetic, 5 plus 4 is always 9, right? It'll never be anything else. And so that barcode should produce an individual price, right? It should always produce that price. Unless the function that the supermarket's using, in other words, they've changed prices. So they're using a new function, then it should again reliably produce only that one price though. So it needs to be well defined. There shouldn't be any wiggle room there. And so we make that definition the one for a function. It's a relation where each object in the sending set is mapped to at most one object in B. So what we're going to do now is look at some examples of relations, talk about this idea of domain and range, and also make the decision: is the object we're talking about a function or is it not? Okay, so let's consider some examples here. So we say determine the domain and range and we're going to decide, is the relation a function? Now we could give a diagram like I did up above. Another way to do it, which is a little more compact, is to give your relation as a list of ordered pairs. So for example, we might have the relation 1 goes to 5, 2 goes to 4, uh, 3 goes to 4, 4 goes to 6, and 5 gets mapped to 2. So there are 5 relationships here for this particular relation. 1 gets sent to 5, 2 gets sent to 4, 3 gets sent to 4, 4 gets sent to 6, and 5 gets sent to 2. So there's two parts to the problem. We want to figure out the domain, and we want to figure out the range. So domain, remember, is the set of objects that we're uh, assigning to things, right? In other words, the input in these ordered pairs. And here we can see that the domain in this problem would simply be the set 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. And then we turn to the output, which is the range. The output values. We see we have a 5, we have a 4, we have a 4, we have a 6, and we have a 2. So the range here would be, like writing them in order, 2, 4, 5, and 6. Okay. 2, 4, 5, and 6. Then we come to the question, does this qualify as a function? Does this satisfy the restrictions that a function puts on a relation? Now, some people will look at a problem like this and see the 2 going to 4 and 3 going to 4 as a problem. Okay, but the function requirement says each thing in A goes to at most one thing in B. And you see, that's happening here. 1 only goes to 5. 2 only goes to 4. 3 only goes to 4. 4 only goes to 6. 5 only goes to 2. It's okay if different things go to the same number. That doesn't violate the condition. At most, 1 output for each input. And so, yes, this actually is a function. So we would say that, yes, this is in fact a function. Okay, so let's take a look at a second example here. Same idea. We're given a list, call it R, for a relation. And let's say in this problem, 1 goes to 3, 2 goes to 7, 3 goes to 3, 5 goes to 1, and 2 goes to 5. Once again, we want to talk about the domain, and we want to talk about the range. You might want to pause the video for a minute and try to write out what you think the domain and range should be. Okay, so let's see what you have agrees with what I find here. So my domain would just be 1, 2, 3, 5. No reason to repeat that 2. When we write a list, we just write it down one time. So that would be my domain, 1, 2, 3, and 5. And then my range would be my output values, which writing them in numerical order would be 1, 3, 5, and 7. Okay. Now the question is this thing a function? Does it break any rules? Well, the fact that 1 goes to 3 and 3 goes to 3, that's not a problem. We said above that was okay. But there's a problem here. And that is that 2 is getting sent to both 5 and 7. Right? And that's not allowed if we're going to have a function. So this is not a function because it is not well defined. Right? 2 has 2 different answers. And a function should produce only one answer. Okay, so that's with a list there, checking out from a list whether something is a function. Also kind of understanding this idea of domain and range. Now we turn from a list like that to what we're really going to be dealing with are equations and graphs. So we ask the question here, determine if the equation is a function. Determine if the equation is a function. We're going to look here at 2 examples here. Consider the equation y equals x squared plus 3x plus 4. We want to ask, is this a function or not? Is this a function or not? Is this a function or not? Well, think about this. We're asking a question for a given x value. If we pick a number for x and put it in for y, is it possible to get more than one answer? Well, let's think about what we're going to do for it. pick a number like 5, for example. If we square that, whatever number it is, 5 in our example, it's always going to give me the same answer. 5 squared in this case would always be 25. 5 times 3 will always be 15. 25 and 15 will always be 40. And when we finally add 4 onto that, 40 plus 4 will always be 44. And that's true for 5, and it's true for any other number, right? Squaring only produces one answer. When you square a number, you're going to get that answer. Multiplying by 3, and then the rest of that's all addition. So no matter what number I put into this is always going to produce that answer for that number. And so this thing passes the test of being a function. This thing passes the test of being a function. On the other hand, consider an equation like this. X plus y squared equals 4. Let's begin by trying to solve this equation for y. Right? Because we're going to try to see, given an x value, can we get different answers for y? So not solve for x, solve for y. So if we take that equation and try to solve for y, first thing we would do is bring the x over to the other side. You'd get 4 minus x. Right? And then we would apply square root to get y by itself. But since that's a y squared, we have to bring in a plus or minus. So we're going to get y equals plus or minus the square root of 4 minus x. And it's that plus or minus that's involved there that tells us that we're not dealing with a function. This is not a function. Right? This is not a function. Okay, because of that plus or minus that's slipped its way in there, this thing will not be a function. This thing will not end up being a function. And so that's what we're going to kind of look for the problems that we're dealing with. Can I solve it for y and have it just y equals without plus or minuses? The actual problem overall becomes more complicated than that. Actually becomes a little more complicated than that, but that's where we're going to leave it. That's going to be sufficient for us. That's going to be sufficient for us. Beyond that, we're not going to get any more complicated than that. So the problems that you're going to run into where they're asking you if an equation is a function, you're basically looking, can I solve it for y without having to introduce pluses and minuses? If we can, then it will be a function. And if not, then it's not a function.